Section 6.2, exponential functions and graphs. In this section, you're going to graph exponential functions, and you're going to graph exponential functions using transformation. First, let's look at the characteristics of the graphs of the parent function, f of x equals b to the x power. An exponential function of the form f of x equals b to the x power, where b is positive and it's not equal to 1, has these characteristics. This function, basically this graph right here, if you take a look at it, this graph first it's a one-to-one function because it passes the horizontal line test, as you can see here. If you make horizontal lines, it just cuts the graph only once, so that will mean the function is one-to-one function. The second characteristic is the horizontal asymptote is the x-axis in this case, which is this line right here, also known as y equals to 0. The domain of this function is from negative infinity to positive infinity. As you can see, the graph is smoothly moving from left to right with no cuts, so it goes from negative infinity to positive infinity. Another characteristic is the range of this function is from 0 to positive infinity, as you can see, because the x-axis is an asymptote, is a horizontal asymptote. So in that case, we're not going to include the 0. So it's going to be from 0 to positive infinity, x exclusive of the 0. And the x-intercept, we do not have any x-intercepts because the x-axis is actually a horizontal asymptote, as you see here. So there is no x-intercepts, but the y-intercept is 0 and 1. That is 0 and the initial value, in this case a is equal to 1. If you look at that and compare it to the function f of x equals to a times b to the x power, you notice that a is equal to 1 in this case. Also, you will notice that the function increases if b is positive. So if b is a number bigger than 1, then the function is going to be increasing or a growth formula. But if b is between 0 and 1, that is bigger than 0 and less than 1, so it's positive, but it's a fraction less than 1, then the graph is going to turn into a decay function with the same characteristics, basically, except for the increasing and decreasing. So it is decreasing if b is less than 1, and I have to be strict here, and I have to include also b is greater than 0 and less than 1, although it is given in the original here, in the original description, but I have to reiterate. So these are the basic characteristics of the parent function, which is f of x equals to b to the x power. Graphing transformations of exponential functions. Transformations of exponential functions behave similarly to those of the other functions that we studied before. Just as with the other parent functions, we can apply the 4 types of transformations, that is shifts, reflections, stretches, and compressions, to the parent function f of x equals to b to the x power, without loss of the shape. For instance, just as the quadratic function maintains its parabolic shape, when shifted, reflected, stretched, or compressed, the exponential function also maintains its general shape regardless of the transformation applied. So to help understand this concept, I'm going to do some examples here. We want to graph the following function. So the following function, the first one is 2 to the x power plus 1. In order to help me graph the transformation, I will use the table of values. So when x is equal to 0, I will have 2 to the 0 power plus 1. That's 1 plus 1 is 2. To apply 1, you get 2 plus 1, which is 3. And then if x is equal to 2, you get 2 to the second power. That's 4 plus 1 is 5. And then 2 to the third power is 8 plus 1 is 9. 2 to the negative 1 is equal to 1/2 plus 1, that is 1.5. 2 to the negative 2 is 1/4 plus 1 is 1.25. And then 2 to the negative 3 is 0.125 plus 1 is 1.125. And then I'm going to plot these points. At 0, we have 1. So that is basically the y-intercept. It changed. And then at 1, it's equal to 3. And then at 2 is equal to 5. And then at 3, it's equal to 9. And then at -1, it's equal to 1.5. 1.5 is approximately here. And then at -2 is 1 1/4. And at -3, it is 1 point, it's very close to 1. So as you can see, that is the general shape. And the graph of the function is going to look something like this. It's going to keep decreasing. Okay. The important characteristics here is the y-axis, or the y-intercept, is 0 and 2. That is the important point in this case. So in this case, as you can see, the parent function is 2 to the x power. It usually cuts the graph here at this point. So I'm going to sketch the parent function. As you can see, the graph shifted up 1 unit. So I predicted that because the transformation here is a vertical shift. So it moves up 1 unit. In the second transformation here, we would expect the graph to shift to the left 1 unit. So it's going to shift to the left 1 unit. Okay, it's not going to show it's not a prominent change, but you will see the change just based on the y-intercept, because that is the most prominent characteristics of the parent function 2 to the x power. So let me graph actually 2 to the x power first. So 2 to the x power is typically crosses through the 0 and 1. It's not precise, but it's very close. So that would be the parent function. And now I'm going to graph the transformation, so I will use the table of values. When x is equal to 0, we have 2 to the 1 power, so it's 2. When x is equal to 1, we have 2 to the 2 power, that is 4. And then when we have x is equal to 2, we have 2 to the 3rd power, which is 8. When we have x is equal to -1, we have 2 to the 0 power, which is 1. When x is equal to -2, we have 2 to the -1, which is 1/2. And then when we have x is equal to -3, we get 2 to the -2, which is 1/4. And then when we have x is equal to -4, we have 2 to the -3, which is 0.125 or 1/8. So I'm going to plot these points. When x is equal to 0, y is equal to 2. And then when x is equal to 1, y is equal to 4. And then when x is equal to 2, y is equal to 8, approximately there. When x is equal to -1, y is equal to 1. When x is equal to -2, y is equal to 1/2. When x is equal to -3, y is equal to 1/4. When x is equal to -4, y is equal to 1/8. So that is the new graph of the function. That is the new graph of the function. Okay. So as you can see here, the graph has shifted to the left. It became closer to the y-axis. You notice the difference between this and that transformation. And you notice that because it moved to the left, now the y-intercept has gone up. And it is a coincidence that it gone up 1 unit in this case, just because the shift was 1 unit as well. But the shift was to the left. But as you can see here, the graph became very close to the x-axis versus this transformation where the graph went up. So the graph was not as close to the y-axis. So you know this is a horizontal shift, not a vertical shift. Reflection. So we know that if we multiply the function by a negative number, the reflection is going to be vertical across the x-axis. So the parent function 2 to the x power, let me make it red, and then I'm going to graph it. It's going to approximately look something like this. That is the parent function. Now we're going to use the table of values to figure out the other function, or the transformed function. So when x is equal to 0, y is equal to -1. When x is equal to 1, y is equal to -2. When x is equal to 2, y is equal to -4. When x is equal to 3, y is equal to -8. When x is equal to -1, y is equal to -1/2. When x is equal to -2, y is equal to -1/4. And then when x is equal to -3, y is equal to -1/8 or 0.125. 0 and -1 is here. We're going to plot them. 1 and -2. 1 and -2 is here. 2 and -4. 3 and sorry, 2 and negative 4 is here. Erase that. And then we have 3 and negative 8, so approximately there. And then we have negative 1 and negative 1/2, negative 2 and negative 1/4, negative 3 and negative 1/8. So the graph is going to look something like this. As you can see, it's reflected over the x-axis or across the x-axis, which is matching this transformation right here. And then we know that if the function is multiplied with a number that is bigger than 1, we know it's a vertical stretch. So this transformation here is a vertical stretch. So I'm gonna graph the original function or the parent function, which is 2 to the x power. It's going to look something like this. It's a sketch, so it's not precise. The most important point is this one, the y-intercept. And then if you apply if you create the table of values for the transformed function, you will get when x is equal to 0, y is equal to 2. When x is equal to 1, y is equal to 4. When x is equal to 2, y is equal to 2 times 4, which is 8. When x is equal to negative 1, x is equal to, y is equal to 2 times 1/2, which is 1. When x is equal to negative 2, y is equal to 2 times 1/4, which is 1/2. And then if you get x is equal to negative 3, the y value is going to be 2 times 1/8, which is 1/4. So these are the points. I'm going to plot them. 0 and 2, 1 and 4. Okay, that is a different scale here. So let me change that to 5. Okay. I will need 1 and 4, so approximately here. And then 2 and 8 is approximately here. Negative 1 and 1. Negative 2 and 1/2. Negative 3 and 1/4. So here is the new graph. And it is vertically stretched by a factor of 2. As you can see, these transformations are not very prominent and they look similar to one another. Unless you have a sensitive eye to the changes happening, you're not going to be able to spot the change very easily, since our focus usually happens on the y-intercept. But however, if you look at the rest of the characteristics, like this part of the function, you will see what is happening exactly. For example, this part is too far away from the x-axis, which means the shift happened upwards. This part, not much of a distance between the x-axis and the graph, that part of the graph that I'm highlighting. So I know that the change happened horizontally. And for this one right here, there is a smaller change, so it moved up a little, but it did not move up a lot like the first part here, so I know that the change is a stretch in this case. The reflection is clear, so you can see the reflection clearly, but the vertical shift and the horizontal shift and the stretches, the vertical stretch are very hard to spot. So here is a summary of the reflections that we did and the stretches and the shifts that we made. You can summarize them in these points basically. So shifts of the parent function f of x equals b to the x power. For any constants c and d, the function f of x equals to b raised to the x plus c and then plus d. Notice how the c affects the x and the d affects the y value. So D is a vertical shift and C is a horizontal shift. These constants shift the parent function vertically D units in the same direction of the sign of D, and we know that from previous units. Horizontally, C units in the opposite direction of the sign of C. So if we subtract C, it's going to move to the right. If we add C, it's going to move to the left. While if we add D, it's going to move up. If we subtract D, it's going to move down. The y-intercept is going to become the point 0 and b to the c power plus d. Basically, we substitute x for 0, and that will give us the y-intercept. The horizontal asymptote is going to be the new line, y equals d, which is basically the vertical shift. The range is going to become also from d to positive infinity, exclusive of d, because that was the horizontal asymptote, but the domain remains the same, which is from negative infinity to positive infinity. And then the stretches and compressions of the parent function f of x equals to b to the x power. So if you have any factor, a is greater than 0, meaning it's positive, then f of x equals to a times b to the x power. It stretches vertically by a factor of a if the absolute value of a is greater than 1. So if it's positive and it's greater than 1, then it's going to stretch vertically by a factor of a. It compresses vertically by a factor of a, that is if a is less than 1, the positive a, of course, and we assume that a is positive. The y-intercept is going to become a0 and a. That is basically if you replace x with 0, you will end up with f of x is equal to a times 1. So that is the y-intercept. The horizontal asymptote is the x-axis, which is y equals to 0. The range is from 0 to positive infinity because the horizontal asymptote did not change and the domain doesn't change and it stays the same all the time. So it's from negative infinity to positive infinity. So these characteristics usually do not change from the parent function by a compression or a stretch. Reflections of parent functions. So reflections of the parent function f of x equals b to the x power. We know that the vertical reflection, if you have f of x equals negative b to the x power, this reflects the parent function f of x equals b to the x power about the x-axis or vertical reflection. The y-intercept is going to become 0 and negative 1. The range is going to shift. It's going to become negative infinity to 0. The horizontal asymptote doesn't change. It's the x-axis or y equals to 0. The domain does not change, which is from negative infinity to positive infinity. Again, these don't change by reflection from the parent functions. Another type of reflection is the horizontal reflection over the y-axis. So if the function f of x equals b to the negative x, then this function is going to reflect the parent function f of x equals b to the x power about the y-axis or horizontally. The y-intercept is going to be 0 and 1, so that doesn't change. The horizontal asymptote doesn't change. It's the x-axis or y equals to 0. The range doesn't change. It's from 0 to positive infinity, and the domain remains the same also at negative infinity and 0. And these do not change from the parent function by reflection, as we mentioned. So the only time the range is going to change is by shifting the parent function to the right and to the left and up and down. Basically, up and down, reflection is going to change the range. However, the domain remains the same for all of them. It's always from negative infinity to positive infinity. Try this. Write the equation for the function described below. Give the horizontal asymptote, the domain, and the range. The function is f of x equals e to the x power, is vertically stretched by a factor of 2, reflected across the y-axis, and then shifted up 4 units. So the new function f of x is going to be the vertical stretching by a factor of 2. It's going to be 2e to the x power. Reflecting across the y-axis means we're going to change the sign of x and then shift it up 4 units. That means we're going to add 4 units to that function. In this case, because it shifted up 4 units, then the horizontal asymptote is going to become y equals 4. So that is the horizontal asymptote according to this rule right here. And the domain remains the same, does not change, is from negative infinity to positive infinity. And the range, according to the first rule here, is going to shift to 4 to positive infinity. So that is the vertical shift to positive infinity.